Hi, welcome to our channel of IGNOU Audiobooks, Indira Gandhi National Open University, School of Continuing Education, SOCE. Master of Science, Food Nutrition, MSCDFSM, revised. Second year. CMFN-004 Advanced Nutrition. Unit-8 Water-Soluble Vitamins, B-Complex Vitamins, and Vitamin C. 8.1 Introduction. Vitamins are essential nutrients found in foods. The requirements are small but they perform specific and vital functions essential for maintaining health. In the previous unit, we learnt about fat-soluble vitamins. Here in this unit, we shall focus our understanding on the another class of vitamins, water-soluble vitamins, i.e. vitamin B complex and vitamin C. You would recall that the major group of water-soluble vitamins is the B-complex group of vitamins. Examples include thiamine, riboflavin, niacin, pyridoxine, folic acid, cyanocobalamin, etc. Vitamin C or ascorbic acid, though categorized under water-soluble vitamins, is different from the B-complex group due to its different nature and mode of action in the body. For fat-soluble, we had done for fat. So let us begin our discussion on the similar lines as we had. Vitamins. Objectives. After studying this unit, you will be able to describe the structure and functions of water-soluble vitamins. Identify the food sources, bioavailability, consequences of deficiency and toxicity. Recognize the recommended amount needed during various physiological stages, and appreciate their importance in relation to other nutrients. 8.2 Water-soluble vitamins, an overview. Vitamins, we already know, are classified by the materials in which they will dissolve. Fat-soluble vitamins, vitamin A, D, E and K, about which we learnt in the last unit, dissolve in fat before they are absorbed in the bloodstream to carry out their functions. Excesses of these vitamins are stored in the liver. Because they are stored, they are not needed every day in the diet. By contrast, water-soluble vitamins dissolve in water and are not stored. They are eliminated in urine. We need a continuous supply of them in our diets. The water-soluble vitamins are the B-complex group and vitamin C. Vitamin B-complex, as the name suggests, comprises of a group of vitamins which essentially are same in many respects. However, in this unit, we shall focus on 6 of these: thiamine, riboflavin, niacin, pyridoxine, folic acid and cyanocobalamin, which along with other B-complex vitamins are considered to be essential from nutrition point of view. You would recall studying the structures of these vitamins in the Nutritional Biochemistry course in Unit 3. All water-soluble vitamins have cyclic ring structures, refer to Figure 8.1, with side chains, and are alcohols, amines or acids. All of them are enzymes, coenzymes or apoenzymes, and have key roles in several metabolic reactions. Vitamin C or ascorbic acid, on the other hand, is a compound that is structurally similar to carbohydrate, refer to Figure 8.1, and plays important physiological roles. Being water-soluble, the B-complex and C vitamins are readily absorbed from the different regions of the small intestine. Water-soluble vitamins are easily destroyed or washed out during food storage or preparation. Proper storage and preparation of food can minimize vitamin loss. Clinical manifestations of deficiency of some B vitamins such as beriberi, cardiac and dry, peripheral neuropathies, pellagra, and oral and genital lesions related to riboflavin deficiency were once major public health problems in some parts of the world. These manifestations have now declined, the decline being brought about through changes in the patterns of food availability and consequent changes in dietary practices. Although many clinical manifestations of B vitamin deficiencies have decreased, there is evidence of widespread subclinical deficiency of these vitamins, especially of riboflavin and pyridoxine. These subclinical deficiencies although less dramatic in their manifestations, exert deleterious metabolic effects. Figure 8.1 Structure of water-soluble vitamins. In our discussion in this unit, we shall focus on the food sources, the mechanism of absorption, storage and elimination, important physiological roles, deficiency diseases, and the concept of bioavailability for each of these vitamins. Let's begin with thiamine, one of the essential B-complex vitamins. 8.3 Thiamine, vitamin B, or anurin. Thiamine is one of the earliest recognized vitamins. The chemical structure of thiamine, figure 8.1, was established by Williams in 1936. The thiamine molecule consists of two linked organic ring structures, a pyrimidine ring bearing an amino group and a sulfur-containing thiazole ring linked to the pyrimidine by a methylene bridge, as shown in red in figure 8.1a, under the thiamine structure. The thiazole ring bears a primary alcohol side chain that becomes phosphorylated to give the thiamine phosphate esters that have cofactor activity. Phosphorylated forms of thiamine, you may recall studying in the Nutritional Biochemistry course, Unit 3 include thiamine monophosphate, TMP, thiamine pyrophosphate, TPP, and thiamine triphosphate, TTP. TTP is the most abundant form and constitutes almost 80% of total thiamine. Let us next study about the food sources of thiamine. Food sources. Thiamine is present in many food products, and depending on the amount of vitamin present, we have categorized the foods as rich, good or fair sources as enumerated herewith. Rich sources: rice polishings, wheat germ, dried yeast, yeast extract. Good sources: whole cereals, whole wheat, millets, raw and hand-pounded or parboiled rice, pulses, soya bean, dried beans, oilseeds and nuts. Fair sources: meat, fish, eggs, milk, vegetables and fruits. Figure 8.2 highlights some of these sources of thiamine. Look up Table 8.2 as well given at the end of the unit, which summarize the rich sources of all water-soluble vitamins. Vitamin B1, thiamine, is found in fortified breads and cereals, fish, lean meats and milk. Next, let us learn about the metabolic fate of thiamine. Absorption, storage and elimination. After a meal, thiamine is found in the intestine in the free form. Its absorption involves two mechanisms, both active and passive. At lower intraluminal concentrations of 1 to 2 mol/L, thiamine is absorbed by an active sodium-dependent carrier-mediated system. This mechanism involves phosphorylation. At a higher concentration, passive diffusion occurs. Thiamine is absorbed primarily from the upper jejunum by diffusion and by an active transport mechanism, but can also occur in the duodenum and ileum. After absorption, only a small part passes into circulation as free thiamine, while a greater part is converted into thiamine pyrophosphate, TPP, in the liver and intestinal mucosa with the help of the enzyme thiamine kinase and ATP. A small quantity of thiamine is also converted into thiamine triphosphate, TTP. Thiamine is transported in blood by facilitated diffusion in erythrocytes in both free and phosphorylated forms, and in plasma as free thiamine and TMP. Thiamine or its phosphorylated derivatives are present in negligible amounts in various tissues. Thiamine is excreted in urine. What is the role of thiamine in our body? Surely, you must be aware of the significant role of thiamine. Read the next subsection and refresh your knowledge. Functions of thiamine. Thiamine has a key metabolic role in the cellular production of energy, mainly in glucose metabolism, i.e., it helps the body cells convert carbohydrates into energy. Thiamine is also essential for the functioning of the heart, muscles, and nervous system. All these functions of thiamine are elaborated in this section. Before you read this section, we suggest you look up section 4.9 in Unit 4 in the Nutritional Biochemistry course. This will help you understand the functions of thiamine as an coenzyme better. So get started. We begin with the regulatory function of thiamine. 1. Regulator of enzyme activity. Thiamine regulates the enzymes involved in carbohydrate metabolism. These are A. Pyruvate dehydrogenase, which provides a key link between glycolytic pathway and citric acid cycle. B. Acetobutyrate dehydrogenase in citric acid cycle and transketolase involved in pentose phosphate pathway. C. Each enzyme contains a decarboxylase moiety that binds TPP at the active site, a lipoic acid binding moiety, a flavoprotein, and one or more regulatory components that toggle the enzyme complex between the active form and the inactive form. Ketoacid. D. A fourth thiamine-requiring enzyme is a branched-chain ketoacid-requiring enzyme is a branch-CH dehydrogenase, which plays a role in the metabolism of branched-chain amino acids. 2. Coenzyme in enzyme catalyzed reactions. Thiamine functions as the coenzyme thiamine pyrophosphate, TPP, in the metabolism of carbohydrates and branched-chain amino acids. Specifically, the AMG-coordinated TPP participates in the formation of acetols, e.g. among hexose and pentose phosphates as described in the reaction given at point 4 below, as catalyzed by transketolase, and in the oxidation of aceto acids, e.g. pyruvate, acetobutyrate, and branched-chain aceto acids, by dehydrogenase complexes, refer to reaction 2 and 3. Hence, when there is insufficient thiamine, the overall decrease in carbohydrate metabolism and its interconnection with amino acid metabolism via aceto acids has severe consequences, such as a decrease in the formation of acetylcholine for neural function. Look at the screen. 3. TPP and TTP are vital for the nerves and cardiac tissues. TPP and TTP are interconvertible and are involved in carbohydrate metabolism. As discussed above, when there is insufficient thiamine, the overall decrease in carbohydrate metabolism and its interconnection with amino acid metabolism via aceto acids has severe consequences, such as a decrease in the formation of acetylcholine for neural function. Thus, deficiency in the tissues affects energy metabolism in nervous tissue and cardiac muscle. 4. Role in the conversion of carbohydrate to fats. Thiamine helps in the initial steps of fatty acid and sterol production. In this way, thiamine also helps convert carbohydrate to fat for storage of potential energy. Having looked at the functions, next let us consider the bioavailability aspect for thiamine. Bioavailability of thiamine. Thiamine is readily available from the gut from food sources as thiamine phosphate esters. Drugs and alcohol abuse may interfere with thiamine absorption and impair thiamine availability. Compared with most other vitamins, thiamine deficiency is seen more rapidly when low intake is encountered. Since thiamine is lost in cooking and is depleted by use of coffee, tannin from black teas, nicotine and alcohol, it is necessary to ensure that intake of thiamine is optimal. What would be the consequences of decreased intake of thiamine? The next subsection focuses on this aspect. Deficiency of thiamine. Thiamine deficiency causes the disease beriberi in human beings, which has been classically considered to exist in dry, paralytic, and wet, oedematous forms. The early clinical features are anorexia and dyspepsia, associated with heaviness and weakness of the legs. There is tenderness of the calf muscles on pressure with complaints of pins and needles pain and numbness in the legs. The knee jerks are usually sluggish but occasionally slightly exaggerated. The subjects feel weak and get easily exhausted while working. If not treated, the subjects may develop polyneuritic beriberi, that is, inflammation of many or all of the peripheral nerves. A detailed discussion on the different forms of beriberi follows. 1. Wet beriberi. Oedema is the important feature of wet beriberi. It may develop rapidly and involve not only the legs but also the face, trunk and serous cavities. Palpitation and breathlessness are present. The calf muscles are frequently tense, slightly swollen and tender on pressure. The veins of the neck are distended and show visible pulsations. The diastolic blood pressure is low and systolic is high. The pulse is fast and bouncing. The heart becomes weak and death occurs due to heart failure. 2. Dry beriberi. Early symptoms are similar to those found in wet beriberi. The muscles become progressively wasted and weak and walking becomes difficult. The emaciated subject needs the help of sticks to stand and walk and finally becomes bedridden. If not treated, the patients will die. Beriberi occurs in human milk-fed infants whose nursing mothers are deficient. Let us get to know about the infantile beriberi. 3. Infantile beriberi. Infantile beriberi is commonly seen in many Southeast Asian countries where the diets consist mostly of polished rice and are deficient in thiamine. The occurrence of beriberi is due to A. Inadequate thiamine intake, related mainly to poor thiamine content of breast milk, and B. Consumption of overmilled rice, deficient in thiamine by the mother. The disease in infants is generally acute in onset while the chronic forms of the disease are seen in late infancy and childhood. Two types of infantile beriberi are known. These are I. Cardiovascular type and 2. Neuritic type. I. The cardiovascular type, where it manifests itself in babies between the ages of 2 and 4 months. The onset is acute with classical signs and symptoms of congestive cardiac failure, tachycardia, dyspnea, enlargement of the heart, elevated venous pressure, enlarged tender liver, edema and oliguria. In some infants, cyanosis and pulmonary edema may develop rapidly and death may ensue in a matter of few hours. 2. The neuritic type, dry. It is also referred to as Wernicke-Korsakoff syndrome or cerebral beriberi. It shows typical manifestations of peripheral neuropathy. Tenderness of calf muscles, diminished tendon jerks. The accent is predominantly on the central nervous system, CNS, with sensorial alteration, irritability, apathy, drowsiness, and coma, signs of raised intracranial tension, staring expression, and varying degrees of neurologic deficit. Besides occurring in infants, beriberi also occurs in adults with high carbohydrate intakes, mainly from milled rice, and with intakes of antithiamine factors, such as the bacterial thiaminases that are in certain ingested raw fish. Beriberi is still endemic in Asia. In relatively industrialized nations, the neurologic manifestations of Wernicke-Korsakoff syndrome are frequently associated with chronic alcoholism in conjunction with limited food consumption. Some cases of thiamine deficiency have been observed with patients who are hypermetabolic, are on parenteral nutrition, are undergoing chronic renal dialysis, or have undergone a gastrectomy. Thiamine deficiency has also been observed in people with chronic alcoholism. We have studied the deficiency symptoms of thiamine so far. What about toxicity related to excess ingestion of thiamine? Let us find out. Toxicity. Thiamine toxicity is not a problem because renal clearance of the vitamin is rapid. Since the body stores of thiamine are very low, we must ensure adequate daily intake. What are the requirements for thiamine then? Let us get to know this next. Recommended dietary allowance, RDA. Thiamine, as it must be clear by now, is needed mainly for the metabolism of carbohydrate, branched-chain amino acids, fat and alcohol. Because the requirements increase as energy expenditure increases, thiamine requirements are expressed as ratios to food energy. ICMR 2020 recommends the requirement of thiamine for men as 0.6 mg 1000 kcal and for women 0.8 mg per 1000 kilocalories. Look at Table 8.1, which presents the current recommendations for thiamine requirement for different age and physiological groups. Table 8.1, ICMR recommended dietary intakes for thiamine across age. Look at the screen. Because thiamine facilitates energy utilization, its requirements have traditionally been expressed on the basis of energy intake, which can vary depending on activity levels. You may have noticed that the requirements increase in case of pregnancy and lactation owing to increased energy demands. How do we get to know then about the thiamine status in our body? The criteria for assessment are highlighted next. Criteria for assessment of thiamine status. Thiamine status has been assessed by measuring urinary thiamine excretion under basal conditions or after thiamine loading, transketolase activity, and free and phosphorylated forms in blood or serum. Let us understand these assessment criteria. 1. Determination of erythrocyte transketolase (ETK) activity. The enzyme transketolase requires TPP for its activity, for the metabolism of pentose phosphate sugars, as described under the functions earlier. ETK activity is expressed as basal, without TPP activity, ETK, or as the difference between stimulated and basal activity as a percentage of basal activity. In thiamine deficiency, the enzyme activity is reduced, decreased ETK, and a small part of the added pentose phosphate disappears. When TPP is added, ETK activity is increased. The percent increase in ETK activity due to added TPP, as indicated in the table 8.2, is an index of the degree of thiamine deficiency. Table 8.2, Determination of erythrocyte transketolase activity. 2. Urinary excretion test. The urinary excretion of thiamine is an index of recent dietary intake of the vitamin. Hence, determination of thiamine in urine samples, 4 hours after the administration of a 5 mg dose of the vitamin, for a period of 24 hours, is a reliable index of thiamine status. An excretion value less than 20 micrograms is indicative of thiamine deficiency. 3. Estimation of blood thiamine levels. The levels of free thiamine and its phosphoesters in whole blood and erythrocytes is measured using high-performance liquid chromatography methods. This measure gives a good indication of thiamine status. We end our study of thiamine now. The interaction of thiamine with other nutrients is another aspect we would like to review in this unit. This aspect is covered separately in section 8.10 at the end of this unit, where the interaction of all the water-soluble vitamins are taken up in general. So now we move on to the next water-soluble vitamin, i.e. riboflavin. 8.4 Riboflavin. Riboflavin, vitamin B2, a water-soluble vitamin, was discovered in milk as a pigment possessing a yellow-green fluorescence as early as in 1879. However, its role in our body was identified much later. The name riboflavin was given to this vitamin in view of the similarity of a part of its structure to that of the sugar ribose and because of its relation to the general group of flavins. Riboflavin and its coenzyme derivatives are isoalloxins, i.e. they contain a pteridine ring with a benzene ring fused onto it. The side chain is a C5 polyhydroxy group, a derivative of ribitol, a pentahydroxy compound, as illustrated in figure 8.1b. You would recall studying in the nutritional biochemistry course that riboflavin has two major coenzyme derivatives, namely flavin mononucleotide, FMN, and flavin adenine dinucleotide, FAD, which is formed by the combination of FMN with one molecule of adenosine triphosphate, ATP. Let us begin our study of riboflavin by recapitulating our knowledge about food sources of riboflavin. Food sources. The food sources of riboflavin include rich sources, liver, dried yeast, egg white, milk powder, kidney, heart. Point good sources, whole cereals, millets, pulses, green leafy vegetables, all seeds and nuts, meat, fish, eggs and milk. Times fair sources, milled cereals and cereal products, roots and tubers, other vegetables and fruits like beans, bingals, papaya, etc. Below are some important sources of riboflavin. Look up table 8.2 as well given at the end of the unit, which summarize the rich, good and fair sources of all water-soluble vitamins. Vitamin B2, riboflavin, is found in cereals, nuts, milk, eggs, green leafy vegetables, and lean meat. Absorption, storage, and elimination. Riboflavin is absorbed from the small intestine through the portal vein and is passed to all tissues via general circulation. Absorption occurs in the upper part of the gastrointestinal tract by specialized transport involving a phosphorylation-dephosphorylation mechanism more than by diffusion. This process is sodium-dependent and involves an ATPase active transport system. Delaying intestinal transit time may result in an increase in the total amount of riboflavin absorbed from the intestine. Intestinal uptake is increased in cellular riboflavin deficiency and decreased with a high riboflavin status. Riboflavin is also synthesized by intestinal bacteria and then absorbed by the colon. This riboflavin produced by bacterial synthesis also contributes to overall riboflavin nutrition. Transport of riboflavin involves loose binding to albumin and tight binding to a number of globulins, several classes of immunoglobulins, IgA, IgG, and IgM. Riboflavin is not stored in the body. A major part is excreted in urine and the rest is broken down in the tissues. Next, let us learn what is the role of riboflavin in our body. Functions. The role of riboflavin in human metabolic processes and in maintaining good health is highlighted herewith. 1. Precursor of coenzymes. The major function of riboflavin is to serve as the precursor of the coenzymes FMN and FAD and of the covalently bound flavins. These coenzymes are widely distributed in metabolism. The role of FMN and FAD as part of enzymes or as coenzymes are shown in Table 8.3. Enzyme. Table 8.3. Role of FMN and FAD. Look at the screen. 2. Role in respiratory chain. Riboflavin catalyzes numerous oxidation-reduction reactions. Conversion of riboflavin to flavin mononucleotide, FMN, and then to the predominant flavin adenine dinucleotide, FAD, occurs before these flavins form complexes with numerous flavoprotein dehydrogenases and oxidases. The flavocoenzymes, FMN and FAD, participate in oxidation-reduction reactions in metabolic pathways and in energy production via the respiratory chain. 3. Drug and lipid metabolism. Flavoproteins catalyze dehydrogenation reactions, as well as hydroxylations, oxidative decarboxylations, deoxygenations, and reduction of oxygen to hydrogen peroxide. 4. Antioxidant activity. Flavoproteins also have powerful antioxidant activity from their role as precursors to FMN and FAD. Among the FAD-requiring enzymes, glutathione reductase is involved in the glutathione redox cycle and provides a major protective role against lipid peroxides. 5. Protective role. Riboflavin protects the octodermal tissues and prevents lesions of the skin, eye and nervous system. Riboflavin ameliorates cardiac damage and also has antimalarial effects. 6. Regulatory functions. Riboflavin is concerned with the regulatory functions of some hormones involved in carbohydrate metabolism. 7. Other functions. Riboflavin interrelates with other B vitamins, notably niacin, which requires fat for its formation from tryptophan, and vitamin B, which requires FMN for conversion of the phosphates of pyridoxine and pyridoxamine to the coenzyme pyridoxal 5-phosphate, PLP. Riboflavin deficiency slows down the uptake of pyridoxine and decreases the conversion of pyridoxine to its metabolites. Before we move on to the study about the deficiency and toxicity of riboflavin, let us get to know about the bioavailability of riboflavin from the diet. Bioavailability. Riboflavin availability is sodium-dependent. Prolonged contact of dietary riboflavin with the absorptive surface of the intestinal mucosal cells increases the bioavailability of riboflavin. Intestinal uptake is increased in cellular riboflavin deficiency and decreased with a high riboflavin status. Diets high in psyllium gum decrease absorption, whereas antacids, as well as the mere presence of food increase absorption. Metals such as copper, zinc and iron, drugs, caffeine and saccharin and vitamins such as nicotinamide and ascorbic acid, tryptophan and urea form chelates and complexes with riboflavin and efemin and thus affect bioavailability. Pregnancy induces the formation of proteins which bind flavins. Bioavailability of riboflavin in foods, mostly as digestible flavocoenzymes, is excellent at nearly 95%, but absorption of the free vitamin is limited to about 27 milligrams per single meal or dose in an adult. D. Pyridoxine. Pyridoxine is involved in glyconeogenesis through its action in transaminase reactions. Low levels of pyridoxine impair glucose tolerance. The coenzyme form of vitamin B, or pyridoxal phosphate, is responsible for all non-oxidative enzymic amino acid transformations and catalyzes reactions such as decarboxylation, transamination, racemization. PLP has a key role in lipid metabolism, and vitamin B deficiency lowers body fat, liver lipid levels, and impairs degradation of lipids. E. Ascorbic acid. The biologically active form, ascorbate, is a cofactor or co-substrate for 8 isolated enzymes involved in hydroxylation of amino acids, metabolism of tyrosine, etc. It protects lipids, protein and membrane structures from oxidative damage. It also regulates protein translation and gene transcription. Since ascorbic acid closely resembles glucose, most mammals can synthesize ascorbate from glucose. However, man lacks the terminal enzyme in the biosynthetic pathway and hence must ingest ascorbic acid to survive. F. Leucine. Excess of the amino acid leucine in the diet antagonizes the function of vitamin B and impairs the conversion of tryptophan to niacin. 2. Interacting with other vitamins. A. Ascorbic acid and other vitamins. Ascorbic acid synthesis is diminished in thiamine and riboflavin deficiency. Vitamin A also plays an important role in the biosynthesis of ascorbic acid. B. Thiamine and riboflavin. Thiamine deficiency is accompanied by disturbances in riboflavin metabolism and excretion of riboflavin in urine. C. Vitamin B and other vitamins. Administration of riboflavin, pantothenic acid, and thiamine provide partial protection against seizures in vitamin B6 deficient experimental animals. D. Niacin and other vitamins. Livers of rats fed thiamine or riboflavin deficient diets contain smaller amounts of niacin than normal controls. Treatment of pellagra with niacin precipitates symptoms of thiamine and riboflavin deficiencies, indicating that niacin deficiency is accompanied by secondary deficiencies of thiamine and riboflavin. E. Vitamin B and C. Vitamin B metabolism increases with higher levels of vitamin C intake. Whole blood ascorbic acid levels fall during vitamin B6 depletion and return to normal levels during repletion phase. F. Vitamin B and vitamin B2. Vitamin B deficiency is reported to cause impairment in vitamin B12 absorption in rats. G. Folic acid and vitamin C. Anemia is observed in vitamin C deficient patients. Normochromic, normocytic or macrocytic or megaloblastic anemia has been reported. These conditions responded to ascorbic acid therapy alone or along with folic acid. H. Vitamin E and C. Both vitamin E and vitamin C are powerful antioxidants. They protect biological systems against oxidative damage due to free radicals. Their functions are synergistic to each other. Vitamin C synthesis is reduced in the livers of vitamin E deficient rats, and several vitamin E deficiency symptoms resemble those of scurvy. I. Riboflavin and pyridoxine. Riboflavin deficiency slows down the uptake of pyridoxine and decreases the conversion of pyridoxine to its metabolites. J. Folic acid and vitamin B. For the conversion of folic acid to folinic acid, vitamin B12 is required. Vitamin B12 deficiency causes a rise in unconjugated folates and a marked depletion of intracellular conjugated folates. 3. Interaction with minerals. A. Vitamin C and iron. Ascorbic acid powerfully enhances absorption of non-heme iron and reverses the inhibiting effect of T and calcium phosphate. Iron absorption is directly proportional to the quantity of ascorbic acid present. Ascorbic acid forms a chelte with ferric iron at acid pH and renders it soluble for absorption. B. Vitamin C, iron and cadmium. Toxic levels of dietary cadmium, 5 to 200 ppm, interfere with iron absorption and produces iron deficiency. Supplements of iron and ascorbic acid protect against cadmium toxicity. With low levels of dietary cadmium, supplements of iron and ascorbic acid decreased cadmium uptake in the liver, kidney, and small intestines. Vitamin C, lead, and mercury. Iron alleviates lead toxicity, but ascorbic acid is ineffective. Ascorbic acid alleviates mercury toxicity, but iron accelerates the condition. D. Riboflavin and iron. Riboflavin deficiency is reported to decrease mobilization of hepatic iron and impair absorption of dietary iron.